This PowerPoint is just going to go through some of the physics and basics of physical measurement, which includes going on to look at uncertainties, which is one of the new things for your 3.1 internal. So just reminding ourselves first of all about the base units that you guys are going to be using. You need to make sure all of the time that you're looking at SI units. So, don't use centimetres or millimetres for distance, don't use minutes for time. Okay, we should be sticking to our SI base units. But if you've got any questions about those as you go through the internals, you can ask. Also remembering really important about using correct scientific notation all the way through. So making sure that we're not writing out huge long numbers, make sure that we're using standard form for very large numbers, or if you end up with very small numbers, again, make sure you're using standard form. Examples given to you there. Again, if you're not sure about how to use standard form, you can always go back and have a look in your textbooks, have a look in your notes. But make sure where it's appropriate, we're always using standard form. Along with standard form, there are obviously some prefixes that we may come across. So for very big numbers, you've got tera, giga, mega and kilo. And for very small numbers, pico, nano, micro, milli and centi. So again, make sure we're correctly using prefixes where appropriate along with your standard form. Significant figures always seem to cause a little bit of stress, but as with your externals and internals, correct use of significant figures is also expected. And when we look at uncertainties in a little bit, you'll see how significant figures are extremely important to correctly noting down the uncertainties and the variables, and also when we come on to do some processing later. The reason they're important is exactly as it says here. This is a way of expressing the precision of a measurement. So now we're looking at practicals. It's really important to have a gauge of how accurate we've been, how precise we've been in our measurements. So I'm sure you've seen these rules before, but just running through them again if you haven't. All non-zero digits are significant. If the zeros are between two non-zero digits, they're significant. If the number's less than 1, zeros after the decimal place are non-significant. Zeros after the decimal place and after any non-zero digits are significant. If a number's got no decimal places, then trailing zeros are not significant. So the new part of 3.1 is looking at uncertainties and errors. So when we're looking at investigations, we've always got to comment on how good was our data, how precise, how accurate it was. At level 2, what you're expected to do is just a generalised comment about that. So looking at your line, how well did the line of best fit represent your data? Did it go through the origin if you were expecting it to? Where might the intercept have come from if it didn't? You were just making a general comment. At level 3, we're expected to give these errors a value. It may be something that you can actually almost calculate, or it may be something that is just really almost a very, very accurate estimate of how carefully, how accurately, how precisely you've measured your data. There's always going to be some uncertainty in every measurement you make, and we've seen this a number of times. This is why we never get the same result exactly practically as we do when we look at things theoretically. So now we've got to think about where those uncertainties come from and how we're going to assign a value to them. One of the main areas of uncertainty is how accurate our measuring equipment that we're using is going to be. So what we have to think about is, are we using a piece of equipment which has an acceptable amount of accuracy, or do we need to swap our piece of equipment for something more accurate? It's probably the first line of thought there. Any fluctuations in values, so you guys will have all done experiments in the past where every time you took that particular measurement you got a slightly different answer. Or even sometimes you get, sometimes when you use ammeters, you will get it fluctuating as you're trying to take a reading. Human factors as well, not thinking about reaction time, but things like, did you start the stopwatch exactly at the right time? And those things are more of a judgment, very difficult to judge. I mean, yes, you're going to have a reaction time, but at the end of the day, your reaction time is going to be the same every time you take the measurement. So, you know, probably not in itself an uncertainty. So the first of those points is thinking about which piece of equipment is going to be the most accurate for what we are trying to do. So this question here, which voltmeter would you use to measure the voltage of a car battery? Car batteries are around about 12 volts. So would we use the one on the left, or would we use the one on the right? Hopefully, if we look at those two pieces of equipment, we'll be thinking the one on the left. Because if we look at the one on the left, it only goes up to 15 volts. And if we look at the particular scale that we've got there, it's taking a reading every half a volt. So we could read it to the nearest half volt. Whereas the one on the right goes way up to 300. So each one of those little reading lines that we've got is representing 20 volts. So if we're only measuring 12 volts, so we can only measure it really accurately to the nearest 20 volts. Now, with this idea of looking at the equipment and how accurate it is, we can assign a value to that, and that's called the limit of reading. And this applies to any analog instruments. It also applies to things like rulers as well. So the limit of reading on these types of pieces of equipment is the smallest scale division on the instrument. And then the uncertainty attached to that is half the smallest scale division. So if we look at this as an example, we've got an ammeter here. If we have a look at each of those scale divisions, each one represents 0.2 of an amp. So as we said before, the limit of reading is the smallest scale. So the limit of reading of this piece of equipment is going to be 0.2 amps. Now the uncertainty is half the smallest scale division. So for this one, the uncertainty is going to be 0.1 amps. So if we were going to include that uncertainty in our reading, if we have a look at the scale and you have a look at the value that we've got, we are up to 3.6 amps. However, we can only be as certain as half the smallest scale division. So we can only be as certain as plus or minus 0.1 amps. The other little thing that you have to take into account when you've got these types of pieces of equipment is that you can only be that certain at each end. So really, our uncertainty here should be 3.6 plus or minus 0.2 amps, because you've got an uncertainty of half the limit of reading, but at each end you can only be certain of where the zero line is to the nearest 0.1 amps, and you can only be certain of the reading at the other end to the nearest 0.1 amps. Now, just while we're thinking about that, we always, and we'll come back to talk about this in a little bit, but we always quote our uncertainties to one significant figure only. Okay, and we'll keep returning to that idea as we go through more of this work. So things like rulers, this is something you'll probably use uncertainties for quite a lot. So we have to look, what's our smallest scale division? But we've got an uncertainty at both ends. So our smallest scale division here is 0.5 centimetres. So we can say we can take the reading to the nearest half centimetre, plus or minus 0.5 centimetres. However, on this, we've got uncertainty at both ends. We've got uncertainty at the zero end and uncertainty at the end where we're taking the measurement. So instead of it being half the limit of reading, so half 0.5 centimetres, it is in this case actually going to be the limit of reading. It is going to be plus or minus 0.5 centimetres. There are quite a few occasions in experiments where we're going to have to repeat the measurements, so we're going to have to repeat and average the measurements that we take. When we do this, the uncertainty is the largest deviation from the mean. So you can have a go at this if you've got your calculator handy. Put all those numbers into your calculator and work out what the mean is. So if we do that, we get a mean of 10.18 seconds, sorry. And then we have to look at the values and say, well, where's the largest deviation from that point? So we've got 10.9 at one end and we've got 9.6 at the other. So 9.6 would be 5.8 away. 10.9 is going to be 0.72 away, so that's going to be our largest deviation. So here we would have 10.2 plus or minus 0.7, because the 0.72 will have to be rounded to one significant figure. And then with the actual value, we've only got one decimal place in our 0.7 seconds, so we have to round the actual measurement to one decimal place as well. So uncertainty first to one significant figure, and then we match the decimal places in the actual value. You'll also see another technique being employed here, which is called the half range rule. So that way of doing it, you would look at the range, so 9.6 to 10.9, which gives us 1.3, and you halve that. So that would give you 0.65. Okay. So you could also use the half range rule as well. That's perfectly acceptable. But again, the 0.65 would have to be rounded to one significant figure. So you could round that to 0.7. Effectively, we end up in the same place anyway. So the size of the errors are obviously related to the types of errors, and we've talked about these types of errors before. We've talked about random errors and systematic errors back at level 2. So just to remind you, random errors. So if our measurement is repeated and it's just as likely to be larger or smaller than the true value, for example, a digital voltmeter giving a fluctuating reading, that's going to be a random error. How we can minimize this? By using repeating and averaging. So when you're talking about how did you minimize the errors as much as you could, obviously this is going to be one technique that you use. And then the bit that we couldn't get rid of completely, we're going to account for when we talk about our uncertainty. We can see random errors on graphs. So the smaller the random error, the closer your points are going to be to your line of best fit. The larger the random error, the further away they're going to be from the line of best fit. Where do random errors come from? Could be any change in experimental conditions. If you're doing something with light and the sun goes behind a cloud while you're doing it. It could be something that's dependent on temperature. As the classroom warms up, that could have an effect on your experiment. Fluctuating readings, variations in surfaces. So if you're trying to measure the thickness of something, or you're measuring a diameter, is that diameter of, say, your pipe going to be truly the same, the whole length of the pipe, or would it vary depending on where you measured it? And things like your human reaction time. When we talk about reaction time, we don't mean sort of those things where you try and stop the stopwatch as fast as you can and see what your reaction time is. We're talking about the fact that how well do you judge the start of whatever's happening when you start pressing the stopwatch, and how well do you judge the end of whatever it is you're trying to time. So those types of things will result in random errors. Systematic errors, as we know, is when your measurement is consistently too high or too low. So this could come from a range of things: poorly calibrated instruments, not accounting for zero error at the end of a ruler, not accounting for parallax error. Multiple readings will not do anything to get rid of systematic errors. When we're looking for systematic errors, often that's shown by a non-zero y-intercept when you're expecting one. Okay, sometimes there are other reasons why we get a non-zero y-intercept, and they're nothing to do with systematic errors. But if you do have a systematic error, And it could just be that maybe you should have an intercept, but maybe it's bigger or smaller than you expected. You need to start thinking of what are some of those possible causes. The bad news, I guess, and this is what we have to sort of start quantifying a little bit at level 3. It doesn't matter how good you are at doing experiments, there will always be some errors creeping in there. The question is, A, how do we deal with them to minimize them, make them as small as possible? And then B, the bits that we can't minimize or get rid of, how do we quantify the amount of error that's left in our experiment? So how we deal with them. Identify all of the errors that you've still got, even though you've tried to minimize as much as you should, and don't leave errors in there that you should be minimizing. Okay, so identify those errors and estimate their magnitude. Do everything you can to reduce the magnitude of those errors. Okay, choosing better instrumentation, reducing random errors, collecting lots of data, those types of things. You've gone through all these accuracy improving techniques quite a few times now. Make sure when you're talking about accuracy that it is actually accuracy that you're talking about. We tend to get a bit sloppy with our descriptions of what is accurate, what is an accurate measurement. So an accurate measurement is close to the true value. It's got a small percentage error in the measurement. So an accurate experiment has low systematic errors. The other thing that you are probably sometimes talking about when you say accurate, you probably actually mean precision or being precise. So precise measurements have small random errors. So repeated measurements give really similar results. The more significant figures the measuring device can measure to, the more precise the reading will be. So precise measurements are not necessarily accurate. Accurate measurements are not necessarily precise. Okay, so if we look at this particular example, we've got a ruler here and we're measuring 26.13 centimeters. Sorry. The last digit is an estimate. Okay, we've gone past 26. We know we're past 26.1, but we're not quite at 26.1. We're not quite halfway between 26.1 and 26.2. So we're sort of guesstimating. But the actual precision here is limited by the instrument. If we had something that could measure to the nearest hundredth of a centimetre, then we could be more precise here. So we might want to change our ruler for vernier calipers or for a micrometer. Okay, so make sure if you're not happy with the equipment that you think you've got, you can always ask, okay, what other equipment could I use to measure this? So rounding up, accurate small systematic error, precise small random error, and you guys may have seen this little analogy last year with the archery targets, but it's worth revisiting if you're a little bit confused still between what's the difference between accuracy and precision, and make sure you try and talk about them correctly in your write-ups. So last little example here, this man's height was measured several times using a laser device. That's what that blue and red thing is on his head. All the measurements were very similar and the height was found to be 184.34 plus or minus 0.01 centimetres. This result is very precise, and we can say that because it's got a high number of significant figures and there was a very small range of measurements, so we know that that was very precise. However, precise as it may be, it wasn't very accurate. And when we talk about accurate, how near to you are you to the true value of that thing? And you may or may not have noticed that he was still wearing his shoes. So precise, yes, the measurements were nearly the same every time. Accurate, no, he's still wearing his shoes. So if he took his shoes off, we measured it with a ruler. This time it can only measure it to the nearest centimetre. Accurate, more so this time because he hasn't got his shoes on, and so we're nearest to the real value, but not precise as the last measurement because we're only measuring now to 3 significant figures. So if we want to reduce the effects of random uncertainties, we need to take multiple readings. The average of the reading is taken as the most probable answer, and the uncertainty, as we said, is the greatest deviation from the mean, or you could use the half range rule. So for example, here we can work out the mean, 4.3 centimetres, and we can say the greatest deviation away from that is our 4.5 or 4.1 on the other side, and we get 0.2. And again, you can see if you did the half range rule here, 4.1 to 4.5, you'd get 0.4, halve it, you get 0.2. So if you're going to state you're using the half range rule, that's also fine, it still gives you the same answer. So again, luckily here this has fallen out as one significant figure anyway, and then we just match the decimal places. So just reiterating, number of significant figures gives an indication of the uncertainty of the measurement. Absolute uncertainty, which is what we call it when we're just using the figure, the actual value, is always quoted to one significant figure, and the measurement should be recorded with the same number of decimal places as you've ended up with in your uncertainty. So if we're looking at something like this, greatest deviation 0.023. Okay, so we round that to one significant figure, it becomes 0.02, and then we match the recorded value to 2 decimal places. So if we were going to look at this little example here, the rule is not particularly clear. But we want to record the measurement on the ruler with its uncertainty. So if we have a look at the ruler, our limit of reading is going to be to the nearest millimetre. So half of that is obviously half a millimetre, but we've got that uncertainty at each end, so we're going to have 1 millimetre either side. And if we read off the scale, we're looking at about 4.3. I would say there. Okay, so 4.3 plus or minus 0.1. So the plus or minus shows us the uncertainty in a measurement, and the absolute uncertainty is the same units as the measurement, and it's expressed to 1 decimal place. Okay. So if you think about, and we did talk about this before, if we think about uncertainties in things like timing oscillations, when you can only really time to the nearest hundredths of a second, but the nearest hundredth of a second when you're looking at 20 seconds, if you time multiples of 10, is going to be a lot smaller percentage-wise than your nearest hundredths of a second if you're only recording 1 second each time. Oftentimes we're going to need to do some work with our uncertainties after we have recorded the initial data. So we will occasionally have to look at fractional, or what's sometimes called relative uncertainty as well. Here we just take the absolute uncertainty, so what we've decided as our uncertainty in our value, and divide it by the measurement itself. It doesn't have any unit because it's actually just, it would be centimetres divided by centimetres or metres divided by metres, so it doesn't have any unit. The other type of uncertainty you may have to work out is the percentage uncertainty. So the percentage uncertainty is just the fractional uncertainty or relative uncertainty multiplied by 100%. And that gives us the percentage uncertainty. So if we had a value like the length of the table here in millimetres, absolute uncertainty is just going to be the value itself, so 5 millimetres. Fractional uncertainty is the uncertainty divided by the measurement, quoted to 1 significant figure, and then the percentage uncertainty, fractional uncertainty multiplied by 100%. Now the reason we need the 3 types of uncertainties is because occasionally, if you remember back to level 2, you're going to have to transform your data to give you a straight line, which means you're also going to have to do that transformation on the uncertainties as well. So if we're adding or subtracting quantities and both those quantities have an uncertainty, we have to find the resultant uncertainty in the answer as well. So in this case, whether you're adding or subtracting, you always add the absolute uncertainties of the quantities that we're adding or subtracting. So here we've got one basketball player, 196 centimetres plus or minus 1, and one who's 152 plus or minus 1. So if we're looking at the difference in their height, we're going to do tallest take away shortest and get 44 centimetres. But regardless of the fact that we are subtracting them, we still add the uncertainties together. If you think about it, the reason for this is, if you think about our tall player, the tallest he could be would be 197. Our short player, the shortest he could be would be 151. And that would give us the biggest difference between their heights. Okay, so we're going all the way back to 151 up to 156, which would give us 46 centimetres as a difference. So 44 plus 2 centimetres. If we made our tall player the shortest he could be and our short player the tallest he could be, we'd end up with a difference of 42. So again, 44 minus 2 centimetres. So that's where that uncertainty combination comes from. Sometimes we will have to multiply or even divide when we're doing a transformation. So when we're looking at those uncertainties for this one area of a block, so you'll have the length and the width. Each of those measurements is going to have an uncertainty. And when we multiply those together, or if we're dividing as well, we have to add the percentage uncertainties of the quantities we're multiplying. So to begin with, your measurements may have an absolute uncertainty. You're going to have to change both of those into a percentage uncertainty, and then you have to add those percentages together. Okay, so here's a worked example. So our block's 10 centimetres long and 5 centimetres wide, both with an uncertainty of plus or minus 0.1 centimetre. So we work out the area as we normally would, and then we have to work out the percentage uncertainty in the length and the percentage uncertainty in the width, and then we add those two together. At that point, you could just say it's 50 centimetres squared plus or minus 3%. That's absolutely fine. But you may want to turn it back into an absolute uncertainty because you may want to do something in terms of some graphical analysis a little bit later. So if we work out 3% of 50 centimetres, we get 1.5 centimetres squared. And so we have to equate that to one significant figure, so round it up to 2. So the area becomes 50 plus or minus 2 centimetres squared.